If you've ever looked closely at a large ship from the side, you've probably noticed something strange. Just below the waterline, at the very front of the hull, there's a rounded bulge protruding forward. It looks out of place, almost like an afterthought welded onto an otherwise streamlined design. And if you've never questioned it, that's exactly the problem. Because that bulge isn't decorative, it isn't structural reinforcement, and it certainly isn't accidental. It's one of the most efficient fuel-saving devices ever designed for maritime transport. And understanding how it works requires rethinking what you think you know about drag and water resistance. Today, we're breaking down the bulbous bow, what it does, why it exists, and how a design that looks like it should slow ships down actually makes them faster and more efficient. And I promise, after this video, you'll never look at a ship's bow the same way again. To understand the scale of what we're talking about, consider a modern, ultra-large container ship. These vessels can be over 400 meters long, displace 200,000 tons when fully loaded, and cruise at speeds around 20 to 25 knots. At those speeds, water resistance becomes the dominant force opposing forward motion. The engines must produce continuous thrust to overcome drag. And drag, in this context, isn't just friction between the hull and water. It's a complex interaction of pressure differentials, turbulence, and wave generation. A significant portion of that resistance comes from waves created by the ship itself as it moves through water. And this is where the bulbous bow comes into play. When a ship moves forward, it displaces water. The hull pushes water aside, and that displaced water has to go somewhere. At the bow, water is forced upward and outward, creating a wave that travels along the hull. This is called the bow wave. Simultaneously, at the stern, water rushes back to fill the space left behind, creating another wave pattern. These waves carry energy, and that energy comes directly from the ship's engines. In other words, every wave the ship creates represents wasted fuel. The larger and steeper the waves, the more energy is lost. For a large vessel traveling thousands of miles, even a small reduction in wave-making resistance translates into massive fuel savings. Now here's the counterintuitive part. You might think that adding a bulge to the front of the ship would increase drag. After all, you're increasing the surface area exposed to water flow. But hydrodynamics doesn't work that way. The bulbous bow doesn't reduce drag by making the ship more streamlined. It reduces drag by changing the way waves interact with each other. Specifically, it generates a secondary wave system that interferes with the primary bow wave, partially canceling it out. This phenomenon is called destructive interference, and when done correctly, it can reduce total wave-making resistance by 10 to 15%. On a vessel burning hundreds of tons of fuel per day, that percentage represents millions of dollars in savings over the ship's operational lifetime. Let me explain how this interference works. When the ship moves through water, the bulbous bow, submerged below the surface, displaces its own volume of water. This displacement creates a wave, just like the main hull does. But because the bulb is positioned ahead of the main bow and below the waterline, the wave it creates has a different phase and amplitude compared to the bow wave generated by the upper hull. If the bulb is designed correctly, the trough of the wave created by the bulb aligns with the peak of the bow wave. When a wave trough meets a wave peak, they cancel each other out. The net result is a smaller, flatter wave pattern at the bow. Less wave height means less energy is being transferred into wave motion, and more of the engine's power goes into forward propulsion instead of churning up the ocean. But here's the critical detail. This cancellation effect only works at a specific speed range. The bulbous bow is not a universal solution. It's optimized for the ship's design speed, the cruising velocity at which the vessel spends most of its operational time. At that speed, the wavelength of the bow wave matches the spacing between the bulb and the main hull entry point, and destructive interference occurs. If the ship travels significantly faster or slower than its design speed, the wave patterns shift out of phase. The bulb may still provide some benefit, but the cancellation effect weakens. In extreme cases, if a bulbous bow is installed on a vessel operating far outside its intended speed range, it can actually increase resistance instead of reducing it. This is why you don't see bulbous bows on every type of ship. High-speed ferries, naval frigates, and racing yachts rarely use them. These vessels operate at speeds where wave-making resistance is dominated by other factors, and the added wetted surface area of the bulb creates more frictional drag than the wave interference can offset. Bulbous bows are most effective on large, slow-moving ships, container ships, oil tankers, bulk carriers, and cruise ships, vessels that operate at speeds between 15 and 25 knots and maintain consistent cruising velocities over long distances. The shape of the bulb matters just as much as its presence. Engineers don't just weld a rounded lump onto the bow and call it done. The size, profile, position, and angle of the bulb are carefully calculated based on the ship's hull form, displacement, and operating speed. Computational fluid dynamics software simulates thousands of variations, analyzing how water flows around each design and measuring the resulting wave patterns. The goal is to find the optimal geometry that produces maximum destructive interference at the target speed while minimizing added drag from increased surface area. There are several common bulb shapes. The most traditional design is a rounded ellipsoidal bulb that extends forward and slightly downward from the bow. This is the type you see on most commercial cargo ships. Some modern designs use a more angular, cylindrical bulb with a flattened nose. Others incorporate a slight upward angle to improve performance in rough seas, where the bow may pitch up and down significantly. Each variation reflects a trade-off between wave cancellation, structural integrity, and real-world operating conditions. And speaking of real-world conditions, the bulbous bow doesn't just reduce fuel consumption. It also affects how the ship handles in different sea states. In calm water, the bulb performs as designed, reducing resistance and improving efficiency. But in heavy seas, when the ship is pitching and the bow is repeatedly rising out of the water and slamming back down, the bulb can experience massive hydrodynamic loads. Engineers must ensure that the structure can withstand these impact forces without deformation or failure. This requires reinforced plating, internal bracing, and careful attention to stress concentration points where the bulb meets the main hull. There's also a secondary benefit that's often overlooked. The bulbous bow changes the pressure distribution around the bow. By displacing water ahead of the main hull, it creates a region of higher pressure in front of the ship. This pressure field helps to lift the bow slightly, reducing the tendency for the ship to squat, a phenomenon where the stern sinks deeper into the water as speed increases. Squat can increase drag, reduce underkeel clearance, and, in extreme cases, cause the ship to run aground in shallow water. The bulbous bow mitigates this effect, improving both safety and efficiency. Now let's talk about what happens when things go wrong. Not every bulbous bow installation is successful. In the 1970s and 1980s, when fuel prices spiked and shipowners rushed to retrofit existing vessels with bulbs, many installations were poorly designed. Engineers used standardized bulb shapes without proper hydrodynamic analysis. Ships that were never intended to operate at consistent cruising speeds received bulbs optimized for conditions they rarely encountered. The result was increased drag, higher fuel consumption, and in some cases, structural damage from unanticipated loading. Some vessels had to have their bulbs removed entirely after trials showed they were making performance worse, not better. Even on well-designed ships, the bulb's effectiveness can degrade over time. Marine growth, barnacles, algae, and other fouling organisms attach to the bulb's surface, increasing roughness and disrupting the smooth flow of water. Regular hull cleaning and anti-fouling coatings are essential to maintain performance. Damage from collisions, groundings, or heavy weather can also deform the bulb, shifting its geometry out of the optimal configuration. In those cases, the bulb may need to be repaired or even rebuilt to restore efficiency. There's also an interesting interaction between the bulbous bow and propeller efficiency. The bulb changes the flow of water along the hull, which affects the velocity and turbulence of the water reaching the propeller at the stern. If designed correctly, the bulb can create a more uniform flow field, reducing propeller cavitation and improving thrust efficiency. But if the bulb generates excessive turbulence or disrupts the boundary layer, it can have the opposite effect, increasing vibration and reducing propulsive efficiency. This is why modern ship design treats the hull, bulb, and propeller as an integrated system, not separate components. One final detail worth noting. The bulbous bow is not a modern invention. The concept dates back over a century. Early torpedo boat destroyers in the late 1800s experimented with ram bows, reinforced protrusions designed for ramming enemy vessels. Naval architects noticed that these ships experienced lower resistance than expected, even when not engaging in combat. Further investigation revealed that the submerged portion of the ram was creating wave interference effects. By the 1920s, shipbuilders began deliberately designing bulbs for hydrodynamic efficiency rather than structural impact. The technology was refined through the mid-20th century, and by the 1960s, bulbous bows had become standard on most large commercial vessels. Today, nearly every large cargo ship, tanker, and cruise ship incorporates a bulbous bow. The design has been optimized to the point where computational models can predict performance with extreme accuracy. But the fundamental principle remains unchanged. Use the ship's own motion to generate a secondary wave system that cancels out the primary wave, reducing energy loss and improving fuel efficiency. It's not magic. It's applied hydrodynamics. And it works because engineers understand exactly how water behaves around a moving hull and how to manipulate that behavior to their advantage. So the next time you see a ship with that strange bulge at the bow, don't think of it as an odd design choice. Think of it as a calculated piece of engineering that's saving thousands of tons of fuel every year. Every curve, every angle, every millimeter of that bulb has been optimized to reduce resistance and keep the ship moving efficiently through the water. And that's the real beauty of marine engineering. It's not about making things look sleek. It's about making them work. If you've ever wondered why cargo ships move so slowly, despite having massive engines, I've already covered that in another video.